In this section, we're going to do the Fundamental Theorem of Calculus. So this section is pretty much going to be the same thing over and over and over again, but lots of examples of it. So the Fundamental Theorem of Calculus says that if f is continuous on the closed interval a to b, and g is an antiderivative of f on that closed interval, then the integral from a to b of f of x dx is equal to g of b minus g of a. So we're going to do the same thing as the last section, but we're not going to use all the silly little rules that we have to remember. We're just going to use this one theorem here, the Fundamental Theorem of Calculus. So evaluate each definite integral. The integral from 2 to 5 of 2 dx. So we need to find the antiderivative of f, and our f right here is 2. So the antiderivative of 2 is 2x. Alright, so you can check that because the derivative of 2x is 2. Now, I'm going to evaluate that from 2 to 5. So to denote that, I'm just going to write a vertical bar and then 2 to 5. And then I'm going to substitute in the 5 and the 2, just like the theorem says, g of b minus g of a. So that's 2 times 5 minus 2 times 2, or 10 minus 4, which is 6. Now, if you didn't believe me that this is exactly the same as what we were doing in the last section, you could pull the 2 out front, so 2 integral from 2 to 5 of dx, and then this integral is just 5 minus 2, which is 2 times 3, which is 6. So that's how we were doing this in the last section. Alright, so now let's try another one here. Integral from 1 to 7 of 6x squared plus 2x minus 3 dx. So I need to find all of these antiderivatives. So the antiderivative of 6x squared is 6, and then x to the third over 3. And the antiderivative of 2x is 2, and then x squared over 2. And then the antiderivative of 3 is just 3x. And then I'm going to evaluate this from the 1 to the 7 that's over here. So if I simplify this first, 6 divided by 3 is 2, so 2x to the third, 2 over 2 cancels, so that's plus x squared, and then minus 3x, evaluate it from 1 to 7. Then I'm going to substitute in the 7, so 2 times 7 to the third plus 7 squared minus 3 times 7. Then subtract, and then substitute in the 1. 2 times 1 to the third plus 1 cubed minus 3 times 1. So this is 2 times, what is it? I think 49 times 7, 63, 28 plus 6, 243. So 2 times 243 plus 49 minus 21 minus 2 plus 1 minus 3. So 2 plus 1 minus 3 is 0. And then this ends up being 486 plus 49 minus 21. So the whole thing ends up being, wait a second, this is not quite right, is it? Nope, that is not right. My apologies for that. What is it going to be then? 343. There we go. 343, not 243. So 343. And then 2 times 4, 343 is actually 686. So I was off by 100 here. There we go. So 686 plus 49 is 735 minus 21, and that ends up being 714. There we go. So I didn't have my calculator with me, so that kind of hurt me right there. I had to go back and double check that. But what a time to be alive. Now it's time for another example of this. Again, we're just going to do a lot of examples of finding the antiderivatives and then substituting in the numbers and using the Fundamental Theorem of Calculus. So, example C. Integral from -2 to -1 of u minus 1 over u squared du. So I'm going to rewrite this as u minus u to the -2 because it might be easier for you to find the antiderivative that way. And then the antiderivative of u is going to be u squared over 2. And the antiderivative of u to the -2 is u to the -1 over -1. And I'm going to evaluate that from -2 to -1. Now, if I want to simplify this first, this ends up being u squared over 2 plus 1 over u. Then I can substitute in the -1 for u, and then subtract that from what I get when I substitute in the -2 for u. So that ends up being 1/2 minus 1 minus the -2 squared is 4 over 2 is 2 minus 1/2. So that is -1/2 minus, what is it, 3/2, which is -4 over 2 or -2. So this whole integral is equal to -2. Again, notice that because these are all definite integrals, I'm not putting plus c or anything. I'm just finding the number that this integral is equal to. And yes, integrals, even though we thought about them as area in the last sections, integrals can equal a negative number because integrals and areas are not the same thing. They can be used to find area, but they're not necessarily the same thing. Alright, so let's go to another one. Now, if you remember the last section, the absolute value is a little bit tricky. So I want to draw this absolute value of x minus 3 for you. And it's the absolute value graph that is shifted 1, 2, 3 to the right. So it looks like this. And the sharp corner happens to be at x equals 3. So this ends up being, if you look at it, the part when x is greater than or equal to 3 has a positive slope, so that's the x minus 3. And the part when x is less than 3 has the negative slope, so that's a negative x minus 3 or negative x plus 3. So I need to break this up into the part when x is between 1 and 3 and the part when x is between 3 and 4 if I want the integral from 1 to 4. Now, this first part from 1 to 3 was the part with the negative slope. So that's going to be the negative x plus 3. And from 3 to 4 was this part with the positive slope. So that's the x minus 3. And then I can find each of these individually. So what is the antiderivative of negative x? Negative x squared over 2 of 3. It is 3x. And then I'm evaluating that from 1 to 3. Then the same thing over here. That's x squared over 2, but minus 3x in this case, from 3 to 4. So then if I focus on just this first integral here, I'm going to substitute in the 3. And then I'm going to substitute in the 1 and then subtract these. Alright, so there we go. And then I'm going to add. Now, be careful because this is adding. So I don't want you to get the signs confused. Inside of each of these is going to be subtracting, but we're going to actually add the two integrals together. So let's substitute the 4. So 4 squared over 2 minus 3 times 4. Then here's the subtracting when we substitute in the 3 that's down here. 3 squared over 2 minus 3 times 3. So if I do all of this, I have negative 9 over 2 plus 9 minus negative 1 over 2 plus 3, then plus 16 over 2 minus 12 minus 9 over 2 minus 9. So if I add all of this together, I have, let's see, negative 9 over 2 plus 9, distribute here, so plus a half minus 3 plus 16 over 2 minus 12, distribute here, minus 9 over 2 minus 9. So, well, what is that going to be? 9 minus 9 cancels. And then negative 9, negative 18 over 2, plus 16 over 2, that's negative, what is that? Negative 1. So you have negative, well, you have negative 13 plus 8 plus a half. It ends up being 5 over 2, or 2.5. If you didn't understand my mental math there, that's okay. You can get out a calculator and double check that yourself. So it ends up being 2.5. Alright, very good. So let's try one with the trigonometric functions now. So this is just going to be trying to remember the trig antiderivatives here. So integral from 0 to pi of 2 plus cosine of x. So the antiderivative of 2 is 2x, and the antiderivative of cosine of x is sine of x. And then I'm going to evaluate this from 0 to pi. So I'm going to substitute in the pi, 2 pi plus sine of pi, then subtract what I get when I substitute in the 0. So sine of pi ends up being 0. So 2 pi plus 0, and 2 times 0 is 0, and sine of 0 is 0, so the whole thing is 2 pi. So if you can find the antiderivatives and then substitute in the pi and the 0 and subtract, this isn't too terribly difficult of a problem. So please try to remember all of your antiderivatives. Let's try again. The integral from negative pi over 4 to pi over 4 of secant squared theta d theta. So the antiderivative of secant squared theta is tangent of theta. And I'm going to evaluate that from negative pi over 4 to pi over 4. Then use the Fundamental Theorem of Calculus to get tangent of pi over 4, then subtract what I get when I substitute in negative pi over 4. So this is tangent of pi over 4 is 1, and tangent of negative pi over 4 is negative 1, so 1 minus negative 1 is 2. So that wasn't bad. Again, besides trying to remember the antiderivatives of the trigonometric functions. Alright, let's try some harder ones. Now, these won't be harder except for the fact that we're going to review the U substitution here. So, this one again, like I just mentioned, integral from 0 to 1 of x times square root of 1 minus x squared dx is going to use the substitution. So u is going to be 1 minus x squared, du is negative 2x dx. Then I divide by negative 2 to get du over negative 2 is x dx. So here's what you really need to try to remember. This is from x equals 0 to x equals 1, because these are all in terms of x, 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 x. So if I'm going to use a U substitution, I need to do the U substitution on the limits also. So if x is equal to 0, and I know u is equal to 1 minus x squared, then when x is equal to 0, u is 1 minus 0 squared is 1. And when x is equal to 1, u is equal to 1 minus 1 squared, which is 0. And then x dx, I just found out was du over negative 2. And then I have square root of u right here. So what I'm actually going to do now is I'm going to bring out the negative 1/2 and then integral from 1 to 0. I'm going to rewrite this as u to the 1/2 to make it easier to find the antiderivative. But then try to remember that we cannot have the lower bound, this a equal 1, be a higher number than the upper bound of b equals to 0. So to switch these around, we have to multiply by negative 1. So multiply by negative 1 to switch the a and the b. So that will actually now be a positive 1/2 integral from 0 to 1 of u to the 1/2 du. And then I can find the antiderivative, which is u to the 3/2 over 3/2. So it's 1/2 times u to the 3/2 over 3/2, evaluate it from 0 to 1. Now that messy fraction I don't like, so it's actually going to be 1/2 times the reciprocal, 2/3, u to the 3/2, evaluate it from 0 to 1. Those 2's cancel, so 1/3 u to the 3/2, evaluate it from 0 to 1. Then I'm going to substitute in the 1 and then subtract this from what I get when I substitute in the 0. So it's 1/3 minus 0, which is 1/3. What a time to be alive. Now again, this U substitution can get quite messy, so I'm going to do a couple more of them so that you see how this is done here. But the number one thing that people do forget to do is switch the limits from x values to u values. So please do not forget to do that. Alright, so the integral from 1 to 5 of x over the square root of 2x minus 1. So u will be 2x minus 1. Now remember, these are x values, x equals 1 to 5. So du is 2 dx, and then I'm going to divide by 2 to get du over 2 is dx. Now, if x is equal to 1, then u is equal to 2 times 1 minus 1, which is 1. And if x is equal to 5, u is equal to 2 times 5 minus 1, which is 9. So u is going from 1 to 9. Now, I know the denominator is square root of u, but I don't know what x dx is. Now, I can solve u is equal to 2x minus 1 for x. So u plus 1 is 2x, and then divide by 2. So this is actually u plus 1 over 2, and then dx right here was du over 2. So this will seem messy, but what I'm going to remind you of is that sometimes multiplying by the reciprocal is not a bad idea. So I'm going to rewrite that as square root of u over 1, and then multiply by 1 over the square root of u, and then 1/2 du instead of du over 2. Now, I'm going to bring out the 2 times 2, so that's a fourth. Integral from 1 to 9 of u plus 1 over the square root of u du. And this is still a little bit messy to work with, so I'm going to rewrite it as u over the square root of u plus 1 over the square root of u du. Then, off to the side, because this is a little bit longer, and remember how I said the U substitution ones might take a little bit longer to do. So u over the square root of u is actually u to the 1/2, and then 1 over the square root of u is u to the negative 1/2. So try to get used to working with the fractional exponents and subtracting them in your head mentally, or however you can get yourself to remember how to do that is fine. Now I need the two antiderivatives, so that's u to the 3/2 over 3/2 plus u to the 1/2 over 1/2 from 1 to 9. And then I'm going to actually go ahead and multiply by the reciprocal of 3/2 to get 2/3 u to the 3/2, and the reciprocal of 1/2, which is 2, to get 2u to the 1/2 from 1 to 9. Then I'm going to substitute in the 9, so 2/3. And this is going to be really a lot, so I have to keep the 1/4 out in front. So 2/3 times 9 to the 3/2 plus 2 times 9 to the 1/2, then minus what I get from when I substitute in the 1, 2/3 times 1 to the 3/2 plus 2 times 1 to the 1/2. And I'm not going to do this all out, especially because I'm running out of room, but you should end up with 16 over 3. So if you want to check this to make sure that you know how to enter this in the calculator, it should be 16 over 3. What a time to be alive. Alright, let's try another one. Now, I promise that the next page will be less messy than the one that we just did, but we still will have to remember to do the U substitution. So U is 2x plus 3. And remember, these limits are x values. So if I want the integral from negative 1 to 1 of 1 over 2x plus 3 dx, in U is 2x plus 3. If x is equal to negative 1, U is 2 times negative 1 plus 3, which is 1. And if x is 1, U is equal to 2 times 1 plus 3, which is 5. So I have integral from U equal 1 to 5. And if U is 2x plus 3, that's 1 over U. And du over 2 is equal to dx. So I'm going to bring out this 1/2. And if you recall, the integral of 1 over u du is the natural log of the absolute value of u, and I'm evaluating that from 1 to 5. So that's 1/2 natural log of the absolute value of 5 minus natural log of the absolute value of 1. But natural log of the absolute value of 1 is 0, so this is 1/2 natural log of the absolute value of 5. And if you don't put the absolute value of 5 and just put ln of 5, that's fine, because 5 is a positive number already. So there we go. That one wasn't too bad, but you needed to remember the antiderivative of 1 over u. Let's try again. So we have integral from e to e squared of 1 over x ln of x dx. So let's let u be natural log of x, which might be a little bit strange, but if you think about it, du will be 1 over x dx. Then, so we have 1 over x and then dx. So if x is equal to e, then u is equal to ln of e, which is 1. And if x is equal to e squared, u is equal to natural log of e squared, which is 2. So this is just integral from u equal, actually, what is it? Yeah, 1 to 2 of 1 over u times du. Because the u was natural log of x, and then 1 over x dx was du. So now, this is an antiderivative of natural log of absolute value of u. Evaluate it from 1 to 2. Substitute in the 2. Subtract what you get when you substitute in the 1. But I know absolute value of 2 is 2 and absolute value of 1 is 1. And then the natural log of absolute value of 1 is 0. So this is just the natural log of 2. I don't think that this one was too bad, except for realizing that u should just be the natural log of x. Alright, let's try a couple more examples with u substitution again. So u is going to be used in this problem as well. Integral from 3 to 4 of 3 integral from 3 to 4 of e to the 3 minus x dx. There we go. So u is 3 minus x. Du is negative dx. So negative du is equal to dx. So the same thing here. These are still x values. So if x is 3, u is 3 minus 3, or 0. And if x is 4, u is 4 minus... No, 3 minus 4. 3 minus 4, sorry about that. 3 minus 4, which is going to be negative 1. So now we're in a situation where this lower u value is actually the 0, and the upper u value is the -1. And we have u was 3 minus x, so e to the u, and then dx was negative du. I'm going to bring the negative out in front, this negative, to get negative integral from 0 to -1 of e to the u du. However, I want this a to be lower than the b. So I'm going to multiply by -1 to switch a and b again. So if I do that, this actually eliminates this negative right here. So integral from -1 to 0 of e to the u du. And the antiderivative of e to the u is just e to the u. So when I evaluate that from -1 to 0, I get e to the 0 minus e to the -1. But e to the 0 is 1, so it's 1 minus 1 over e. Hopefully this wasn't too much to take in, but one of the keys to this problem was remembering to multiply by -1 to switch the a and the b around. Alright, let's try again. Integral from 0 to 1 of e to the x over 5 minus e to the x dx. So this will be another u. U is 5 minus e to the x. Du is negative e to the x dx. So I have e to the x dx in the problem, so I want to multiply by the -1 or divide by -1 just to get e to the x dx. Now, when x is equal to 0, u will be 5 minus e to the 0, or 5 minus 1, which is 4. And when x is 1, u will be 5 minus e to the 1, or just 5 minus e. So this isn't going to be a nice one, but I never said, that it would be nice, but it would have been reasonable if we could have had a nice value there, but oh well. So now u was in the denominator, so we have 1 over u times negative du. I'm going to bring the negative out in front, so that's negative integral from 4 to 5 minus e of 1 over u du. Oh, I didn't write the d right there. Sorry about that. Now the antiderivative of 1 over u is natural log of the absolute value of u. So we have negative natural log of the absolute value of u, which we're evaluating from 4 to 5 minus e. Now, here is the real kicker for me, actually. Maybe I should back up, because I don't want anyone to be upset about this. The one thing that I want you to notice, because I was going to go and do this out anyway, just so that you could see what happens, but I want you to notice that 5 minus e, 5 minus e is 5 minus, and e is about 2.718281828. Alright, so if you do that, you get 2.28, something like that. So this is actually a lower number than the 4. So this is technically another situation where you need to multiply by -1 to switch a and b. So this negative actually goes away. So this is technically the integral from 5 minus e to 4 of 1 over u du. And then you can just say this is natural log of the absolute value of u. Evaluate it from 5 minus e to 4. Or natural log of 4 minus natural log of 5 minus e, and then use the log rules to rewrite it as a single log. Alright, so yeah, I was going to do this and then show you that you should have done that, but I figure now at this rate it's easier just to do it this way. So always make sure that, again, you switch the a and the b if you need to. Which it was a little bit harder to see here because 5 minus e isn't a number that you would typically know off the top of your head. Alright, let's try another one. This one is going to be a little bit different. Use the differential equation and the given point to find an equation of the function. So I'm going to rewrite this as a differential. So dy is equal to 4x plus 9x squared over 3x cubed plus 1 to the 3 halves dx. And then I'm going to take the antiderivative on each side. So y is equal to 4x squared over 2. Now, for this guy right here, this is going to be a little bit harder here, but if I let u be 3x cubed plus 1, then du is 9x squared dx. So I have integral of 1 over u to the 3 halves du, or integral of u to the negative 3 halves du. And then if I find the antiderivative, I have to write it as u to the negative 1 half over negative 1 half plus c, because these are not definite integrals because we weren't given a limit of integration, a lower and an upper limit here. If I multiply by the reciprocal, I have negative 2 u to the negative 1 half plus c, or negative 2 over the square root of u plus c, and then I replace the u down here, so negative 2 over the square root of 3x cubed plus 1 plus c. So this is minus 2 over the square root of 3x cubed plus 1 plus c. And now I use this x and y that they gave me, the given point 0, 2. So y was 2, x was 0, and then I can figure out what c is. So that is 0, so 2 is equal to negative 2 over the square root of 1 plus c, or add the 2 to each side, so 4 is c. Whoop, that's 4. So that means that the function is y is equal to, I'm going to simplify 4 over 2 here is just 2. So 2x squared minus 2 over the square root of 3x cubed plus 1 plus c, which is 4. So that is the function that they want. Sorry about that. For whatever reason, all of a sudden my 4s are not coming out very nicely, so I apologize for that. Here we go. I cannot tell you why I cannot draw a 4 right now. There we go. So that is the function today. Alright, now for something a little bit different. Use the Fundamental Theorem of Calculus to evaluate the definite integral of the algebraic function. integral from 0 to 9 of absolute value of x squared minus 5x dx. So what I am going to do for you is I'm not going to actually do this using a calculator, but I am going to graph it, and you could graph this on a calculator. So if I graph this function right here, 1, 2, 3, 4, 5, it looks something like this. Alright, so it's a very... Oh. Now, it's a very strange looking function, and I wouldn't expect you to know what this is off the top of your head. That's why I said that I even would use a graphing calculator for this. But you see that the function is different between 0 and 5 than it is between 5 and 9. So if I want to look at the integral from 0 to 9 of this function, this is one I'm going to have to split up from 0 to 5 and then from 5 to 9. Now, from 5 to 9, we see it's the straight line part, and then from 0 to 5, it's a curved part. Now, this isn't technically a straight line. If you think about it, this is a quadratic or a parabola. So what actually is going on is that you could draw this half of the parabola, and over here and over here is the part of the parabola that's pointing up, and then from 0 to 5 is the part of the parabola that's pointing down. So this is actually a piecewise function. So from 0 to 5, I have the part of the parabola that's pointing down, and from any other value, I have the part of the parabola that's pointing up. So from 0 to 5, I have negative x squared minus 5x dx, and from 5 to 9, I have x squared minus 5x dx. By the way, this is not one that I would normally have you do because it is a little bit harder. Now I'm going to distribute this negative so that I don't forget. So it's negative x squared plus 5x, and this will be x squared minus 5x. Now I'll find the antiderivative, so negative x cubed over 3 plus 5x squared over 2, and then evaluate it from 0 to 5. And I'll find the antiderivatives, which will be x cubed over 3 minus 5x squared over 2, and I'll evaluate it from 5 to 9. And this can get a little bit messy, because if you substitute in the 5, and then you substitute in the 0, and you subtract, and then you substitute in the 5 and the 9, which you still have to do over here. Ooh, this is a lot of substituting of numbers. What a time to be alive. 5 cubed over 3 minus, what is it, 5 times 5 squared over 2. I don't even have room to do this all out by hand, so I'll just tell you that it is 493 over 6, and you can check that on your own. Alright, now let's go on to a different part of the fundamental theorem of calculus, the second fundamental theorem of calculus. This part is actually a little bit easier as long as you understand what is going on. So if f is continuous on an open interval I containing a, then for every x in the interval, the derivative of that integral with respect to x of the integral from a to x of f of t dt is equal to f of x. So as long as this is a to x, the derivative of this is just substituting the x in right here for t. So use the second fundamental theorem of calculus to find f prime of x. So f of x is integral from 1 to x. See how this is 1 to x. So a is equal to 1 and x is still just x of t squared over t squared plus 1 dt. So f prime of x is literally going to be just substituting the x in for these t. So x squared over x squared plus 1. Alright, let's try another one. Here we go. This is going to be f prime of x. Now, see how f of x is integral from 0 to x? It's a number a to just x. That means we're just going to substitute the x right in for t to find the derivative. So that's secant cubed x. Alright, let's try again. This one is not a number to x. It is negative x to x. So this has to be a number down here. But I can split this up into integral from negative x to 0 of t dt plus integral from 0 to x of, did I say t dt or t cubed dt? I think I said t dt, so sorry about that. T cubed dt plus integral from 0 to x of t cubed dt. Now, I'm just doing that because 0 is halfway between negative x to x. So this is a logical way to do this. Now, oh, by the way, another thing is if I look at t cubed, I can sort of see that it looks like this. So this part of the function down here is different than this part because t cubed is symmetric here. Alright, so now what I want to do is make sure that the a, or the 0, is on the bottom, or is my lower limit. So I can do that by putting a negative in front and then switching the 0 and the negative x. And then this one over here, the 0 is already on the bottom, 0 to x of t cubed dt. Now, this is still not quite right because this is x times negative 1, or negative x, and it's supposed to just be x like over here. So what I do is I make sure the negative is in front, but then I substitute in the negative x here when I want to find the derivative. So negative x cubed. But then do you remember the chain rule? The chain rule says when I'm finding the derivative, I need to find the derivative of the inside. So the derivative of what's inside here is negative 1. And then this is just 0 to x, so I can just substitute that x right in and get x cubed. So this ends up being negative times negative x cubed times negative 1, negative x cubed plus x, and the derivative is actually equal to 0. Now, if that chain rule didn't make sense, I'm going to do one more example of the chain rule on the next page, which hopefully will clear it up. So let's try one more. Use the second fundamental theorem of calculus to evaluate the derivative with respect to x of the integral from 5 to x squared plus 9 is sine of t cubed dt. So again, this is a number, and this up here is supposed to be x. But since it's not, what I'm going to do to find the derivative is substitute the x squared plus 9 in for t. So sine of x squared plus 9 cubed. And then I'm going to use the chain rule and multiply by the derivative of this inside function, which is going to be 2x. Now, it's not the derivative of x squared plus 9 cubed, because the cube was not part of the upper limit here. It's just the derivative of this upper limit. So this ends up being, if you want to write the 2x first, 2x sine of x squared plus 9 cubed. Why is that in the wrong spot? So hopefully this all made sense, but that is an overview of the first and the second fundamental theorems of calculus. I sincerely hope that you really enjoyed this. What a time to be alive.